Welcome to the Office Hour with Dr. Alberto Cruz. I am your host, Dr. Alberto Cruz. Today we'll be revisiting the concept of the stack and our previous example for foobar. I don't know if you remember, but at the assembly level we implemented this code, and essentially on a branch and link there is only one register for the link register or return address, and if you have a non-leaf subroutine call, it ends up clobbering the value in x30, causing an infinite loop situation where it will jump into the return address for foo. All right, so let's break out our terminal and attempt to code this and observe what will happen. All right, so here's our terminal. Let's go ahead and code our main. So we need a global main function, and all it's going to do is call foo and then return 0. So this declares a global main function. This is a label that indicates that the next instruction that follows after this should be considered the start of the main function. BL foo is our command, where main just calls the function foo, and these two commands together are our return 0, where we place a 0 in the return register and then execute the return command. Now let's implement foo. Same thing, we'll implement a global function called foo. All foo will do is call bar, and then it will return. All right. Right, we got to label this thing, right? So okay, so you have global foo, instruction that follows is labeled foo, branch and link to bar, and then return. Now finally we have a bar function. We'll label that instruction this time. All this thing does is return, basically. So what'll happen is this instruction here will jump into foo. It'll jump down here. Notice that on a branch and link, what'll happen is it will save PC plus 4 to the register x30, which would be this thing right here. All right. You get into foo, it too calls a branch and link, and what happens is it places PC plus 4 in x30, so PC plus 4 ends up being this, basically. All right. So that works for bar, because when you jump into bar, when you hit this return command, it will return to the register in x30, which is this, right? But once you get back inside of foo, the notion is that it should return into main. However, you've clobbered the value of x30, and it is currently that return, so this code will be forever stuck at the return. Let's see what happens when we compile this thing and try to run it in GDB. So the commands are, I'm going to display all warnings. I'm not going to use any optimizations. I want the output to be main.out, and we're going to want to compile our main.s. All right, it compiled, no errors. Let's go ahead and run this thing and see what happens. All right, so looks like it's just stuck in an infinite loop. I guess if you want to verify in GDB you can, but it'll verify essentially what we've seen, which is that it'll just be stuck. So yeah, that's not great. I suppose what we could do is let's restart GDB. I suppose what we could do is set some breakpoints for foo and bar, for example, if you wanted to just see what happens to the return address. Let's go ahead and run this thing. All right, so it is now stopping at foo. Let's check out our registers here. Info registers will display all of the registers. The one you're going to want to pay attention to is x30. So currently the return address is whatever this value is. I guess we could assume that that is main, right? On entry to foo, that should be PC plus 4 or wherever you need to go to get back to main. All right, but if we continue and we check the same thing here, info registers, and we just keep looking here, notice that that is a different value entirely. All right, so it'll be stuck. All right, so what can we do there? I guess we'll have to implement the stack. So the purpose of this video is our first exposure to the stack, strictly to store the return address. So the steps to using the stack are, if you have a particular subroutine that you know will need to store local variables, what you're going to do is move the stack pointer by a certain number of bytes. Then you have the logic for your function, and just before the return, you are going to move the stack pointer back to where it needed to be. So let's modify foo and bar, all right, but we'll start with foo first. So what we need to do is to move the stack pointer to declare a certain amount of space. I'm going to use a sub command, so we're going to alter the stack pointer by 32 bytes, basically. So why 32? It's just an arbitrary number, all right? And remember here, you're subtracting from the stack pointer because in our depiction of the virtual memory, it grows down. So you need to move the stack pointer to a lower address. It's got a funny sort of situation where it is growing from top to bottom. So you kind of look at it in reverse, all right? So this command allocates 32 bytes on the stack for us to use. So if we need to use any local variable space, we can store it relative to the location of the stack pointer between where the stack pointer currently is and that top location where it was on entry to the function, okay? You're not supposed to modify stuff above that point because it is stack space that was being used by the caller, all right? Don't mess with the caller stack, basically. You consider it reserved, all right? You're not supposed to use the space below the stack because it is considered garbage, all right? You can only really consider the space between the old stack pointer and the new stack pointer as the space that you should be using, all right? So that's the first point there. We allocate a stack. Now we have to make sure that when we're done with the logic of our function, we revert the stack, all right? How do you do that? Well, you add a certain number back to the stack pointer. Anyways, you were the one to move the stack pointer in the first place, so you should just remember the exact amount of space that you move the pointer by. In this example, I move it by 32, and then we move it back by 32. All right. So, anyways, what are we going to use this space for? Well, the return address, right? I think the issue here is that on entry to foo, we have a certain value in x30, and on this call to bar, it clobbers our value of x30. So what we can do is save the return address. So we will store the value of x30 on entry to the function foo, and we'll store it at the stack pointer. All right, so basically we have the stack frame that was moved 32 bytes, and the return address will be just at the bottom of this thing. Okay. Now, one thing to note is that you need to know how much space is being taken up. All right. In this particular example, we only have one item to store on the stack, but in the future, you're going to store multiple items there. So x30 is a 64-bit value. Remember that in ARM, memory addresses are 64 bits. So that's why, it'll take up 8 bytes. So basically, at the bottom of the stack, bytes 0, 1, 2, 3, 4, 5, 6, 7 are the return address. So in the event that you needed other stack space, you'd have to make sure to start at SP offset from 8 in order to avoid clobbering the value that was at the stack pointer. All right. Anyways, so basically what this does, again, is to allocate 32 bytes of stack space to save the return address to the stack. And now, just before return, we are going to load the original version of the stack pointer. Remember, we placed it at SP, so you're now taking whatever was located at SP and moving it back into x30 so that when you jump on the return, it will indeed read that proper value. All right, now let's do the same thing for bar. You might wonder, hey, wait a minute, this is a leaf subroutine. Why would you bother to do all of that? Well, there's this thing called a calling convention, which is a particular set of actions you perform for a subroutine that should always be performed, and saving the return address to the stack is a part of that calling convention. Now I know this seems wasteful, but you know, you'll notice that GCC will do this. It's like a requirement defined by the instruction set architecture itself, the operating system, and then some other standard. All right. Anyways, it's just good practice to do so. So even though bar does nothing, it still allocates 32 bytes of the stack, saves the return address, and literally does nothing, and then pops the stack frame, and then returns. All right. Okay, so what do we expect to see here? Well, main will branch and link to foo. It will enter foo, and then it will allocate some stack space for itself. It'll save x30, which, by the way, x30 should be this move instruction, right? It'll be the instruction after the link. So basically, on this branch and link, PC+4 is this move instruction, and that address would be contained in x30. And what we're doing is we're storing that, basically that location to that instruction onto the stack. All right. When we call bar, notice what happens. Bar has this expectation where it too moves the stack pointer. So you can imagine foo's stack frame being here and bar's stack frame being here. And what will happen is references to local variables for bar should be relative to its own stack frame. It will not modify foo. So this concept that we had saved x30 is a local variable to foo and not bar. All right. Not that we do anything with it anyways, right? So you enter bar, it saves the return address, which should be, by the way, if you're in bar, if you call this branch and link to bar, the PC+4, the next instruction would be this instruction. All right. So that would be the return address that's saved on x30. Okay, so it does nothing basically, and it restores that, and it returns to this particular point. Now, the problem was before that we had lost that value of x30, but because we saved it to the stack, we can return that value from where we had it in our stack frame and place it into x30 so that when we return, it returns back up to wherever the main was, which would be that instruction, this instruction right here. One thing before we compile this thing, the calling convention is so important here. Once you start using the stack, you'll have to basically follow through with it on every instance. This particular example won't even work, by the way, unless you implement the same code we put in bar in the main itself, which is weird to think about. You know, I guess main itself is being called by the supervisor, or rather the operating system, which too expects the stack pointer to be the same value on the return. So basically, if you don't add these two commands to move the stack pointer and save the stack pointer, to move the stack pointer and save the return address, this following example won't work. All right. One other thing before we compile too, in order to show you that foo basically retrieves the same return address, I'd like us to set a breakpoint here, which I will call taco, on that return. So essentially what we're going to do now is compile this thing, and I'm going to set a breakpoint on foo, and then we're going to observe the entry return address for foo, and then we're going to also set a breakpoint on taco, and just to confirm that the return address is the same on entry and on exit, thus solving our infinite loop problem. Let's go ahead and compile this thing. All right, so that ran, and it works just fine. All right, now let's bring it up in GDB to observe the actual values. Set the breakpoint to foo, and we'll set the breakpoint to taco. All right, let's run this thing. So we're stopped at foo. I'm going to display info registers x30 to display only the current return address. So that would be 728. All right, let's continue. So it'll continue. Note that foo will call bar, which would technically clobber the return address, but we saved it to the stack. All right, and then just before taco, we pull the old value off the stack. So if I just double check here, x30 is now the same. Okay, so we actually resolved that infinite loop problem, you can assume that 728 should return somewhere in main. Continue this thing. If you continue this thing, it should get to the point where main is able to exit normally. All right, cool. There you have it, people. Our first example for using the stack. Have a great day, people.